So the next talk is by Zilu Tian, who was from EPFL and is now at the University of Zurich. And she's going to talk about multi-stage, vertex-centric programming for agent-based simulations.
Thank you for the introduction. So the title of my talk today is Multi-Stage Vertex-Centric Programming for Agent-Based Simulations. Some of these terms may sound unfamiliar to a lot of you, such as vertex-centric programming and agent-based simulations, and we'll start by explaining what these are. So what is vertex-centric programming? This is a programming paradigm that makes parallel graph processing simple. So graph processing is central to many real-world applications. Big tech industries like Facebook, Google, they all have at its core some performing graph-based analysis for their products, such as Google Map, obviously. But parallel graph algorithms are very difficult to design in the traditional top-down approach. Imagine, the developers, when they try to write a concurrent program for such distributed graphs, it's really very difficult given the scale. So Prego, which is an internal tool from Google, advocated for this vertex-centric programming paradigm. This really takes a bottom-up approach. So instead of defining a parallel program where you actually need to aggregate certain global information, users define a single sequential program that describes the local behavior of a vertex in the distributed graph. And this local vertex interacts with other vertices to actually perform computations required for a given graph algorithm on a distributed system. And this works surprisingly well and scales to really large-scale graphs. And this programming paradigm has been widely adopted by many open-source frameworks. So Prego is not open source, but Giraffe is an open-source implementation of Prego. And similarly, it's also adopted by GraphX, which is built on top of Spark, and also Apache Flink. The computational model of this vertex-centric programming is based on bulk synchronous parallel. So this is an abstract machine model which basically says the computations of such a concurrent program will proceed in a sequence of supersteps separated by global synchronizations. So per superstep, each core or per vertex in our vertex-centric context, they can process messages from other vertices, perform local computations that update its own state, and send messages to other vertices. It's very simple, straightforward, and this forms the core computational model for Prego and other vertex-centric frameworks. Now, what are agent-based simulations? Well, agent-based simulations are fine-grained modeling. So conceptually, we can imagine that we have many little AIs, each with its own thread and state, and performing some arbitrary computations. So these little agents, they live and interact in such a virtual world. To really understand what agent-based simulation is, it's important to point out what it's not. So we can contrast with the coarse-grained modeling, such as the classic SIR model in academics. So in such classic modeling, people will describe certain simulation behavior as a set of differential equations. So in this case, different variables are described as the changes with respect to time. The problem with such coarse-grained modeling is that it's very difficult if you want to adjust the behavior. So for instance, if you want to investigate, well, now what happens if people actually travel around, right? Or what happens if some new policy is introduced which changes people's contact behavior, right? So if people are now with a quarantine policy, they're staying more time at home instead of interacting with others. It requires non-trivial changes to the differential equation models, but such changes are very simple to adapt in agent-based simulation models. And it's the flexibility of agent-based simulation that really gained its popularity among many domains. So agent-based simulation has been around since 1970s, and it has been widely used in many domains, such as academics, economics, and many others. Of course, we as computer scientists care about it because it's actually a wide open area for us as well. So there are many challenges associated with agent-based simulations that are of relevance to computer sciences, to computer science. So for instance, as a distributed system challenge, it's non-trivial if you want to simulate billions of agents which are, who are actively interacting and communicating with each other. Existing frameworks such as Spark, they are usually optimized for data intensive, where there is basically assumes there is no communication among different data nodes. And the synchronization associated with such systems is also very costly. So to have an efficient execution of such large-scale simulation, it still remains a challenge for distributed systems. It's also an interesting data management challenge, because people don't run simulation just for the sake of modeling, right? People want to answer questions. So given an epidemic simulation, I want to know, okay, what can I do to, say, reduce the number of infected population by half, right? So if I want to evaluate different effectiveness of various policies, people want to have an easy-to-express language that can describe a query language that can directly integrate it into such simulation modeling. It's also interesting for machine learning community where people can really use simulations as complex learning models. And some agents have actually lots of latent variables that contribute to the overall result. But of course, for the focus of the talk today, we will mainly talk about the challenge that's relevant to programming, to the programming language community, and which is the focus of this talk. But there are also like compile optimization opportunities in the domain. So given that this field is very wide open, we'll start by saying what we assume in this in the scope of this paper. So we are assuming that we only consider synchronous agent-based simulations where the semantics, the computational model of such a synchronous agent-based simulation is exactly as defined in the BSP model. All right, so in this case, it's easy to see that, well, an agent can kind of be viewed just as a vertex, right? It's not so much different. You're performing some computation, and then you're communicating with other agents. Given this assumption, how suitable are existing vertex-centric frameworks, such as Prego, Giraffe, GraphX, and Flink, really for agent-based simulations? So can domain scientists just directly take such frameworks and start running simulation? Are we done? Well, we'll start with an example of what does the state-of-art vertex-centric frameworks look like, all right? So users define a single sequential program, right? So in a usually called compute method. And this compute method is repeated code in each superstep during the execution. So the classic example is the PageRank example, where each vertex basically sends its own calculated PageRank value to neighbors and aggregates the values from the incoming links and update its own PageRank value. So here we clearly see that in red, if you want to have different behavior that's dependent on superstep, right? If you say, well, in the first superstep, because I don't really have an incoming message yet, so all I want to do is just send out my message, my value to other vertices, right? If you want to specify this behavior, you really need to add a branch to dispatch on the value of superstep just to describe this behavior. And in the particular case of PageRank, because there is no obvious terminating condition, can kind of just run forever. So if you actually want to say, well, the simulation runs only for 30 supersteps, you have to add a conditional branch to say, look, I'm actually checking for if superstep is less than 30, otherwise I vote halt. So clearly, we can already see that since this particular compute method is repeated code in each superstep, it's kind of inefficient to always compare these branches when you clearly know that in the next round, the superstep value has already changed, right? So there, we see that there is some inefficiency associated with the dispatching overhead, and it really does not scale as the control flow becomes more complex. It's very easy to make mistakes. This particular instruction vote to halt here is specific to Prego or existing vertex-centric programs. So this is a way for a vertex to say whether I'm active or inactive. And the terminating condition is that it will stop when all vertices become inactive. So for the scope of our talk today, we will actually assume that we don't have this instruction. Okay, we're assuming, well, the simulation should just run for a given value as user defined. So this is desirable for simulations because imagine you have an epidemic simulation, right? You can say, well, if a person is infected, then this person wants to remain at home for 5 days without interacting with anyone. But you don't want this simulation to terminate just because if everyone is infected and staying at home. You still want it to run, say, for 200 rounds or something. So we will also assume that we do not have this instruction, vote to halt. Now, as I just explained, so one clear limitation of this is it scales very poorly as the control flow becomes complex. This permits erroneous programs where instructions for different supersteps can be defined at a wrong value. So consider the very simple traffic light example. If you just want to say the color of the traffic light changes as the time proceeds, you can totally define a syntactically correct but semantically wrong program like this, and it will execute. And it's very difficult to debug if you actually allow this to execute in a real simulation. So we want to forbid this. Well, one obvious solution is that we can introduce a binding construct, right? We say, well, the problem of that is we don't have an explicit binding construct specifies what instructions are allowed to execute for a particular superstep. How about we introduce this? So this is a rewrite of the previous example using this binding construct, which we call SC. And we see that now the compute method basically contains what are the instructions that need to be executed in different supersteps as the simulation proceeds. Okay, this seems fine, but it can actually cause code duplication. So it's also the traffic light simulation example is simple enough to illustrate the problem of despite of this erroneous program. It actually if the binding construct can actually cause duplication for more complex program when closures in different supersteps actually need to share instructions. So if we revisit the previous PageRank example and rewrite it using our newly introduced binding construct, we see that instructions highlighted in red are actually repeated in both the closure specified for superstep 0 and for later supersteps. And this duplication is not there when we in the original vertex-centric model, right? So there, we have a conditional branch to check what the current superstep value is, but we didn't have to duplicate these instructions. So to avoid this, we basically let each superstep execute an arbitrary number of closures instead of a single one. And at the end of each such closures, we pass the continuation index. So this is an example of how we change the previous PageRank example with duplicated code into a non-duplicated code version. So we see that this here at the end of the first superstep, we set yield equals true, and then say, well, we should continue with the index 1. And then in the closure for 1, we do not set any yield because this will actually continue with the next superstep. Okay, this seems to address our concern concerning duplicated instruction and erroneous programs, but it seems very complicated and it's not very easy to write. So we really want to generate such closures automatically. And we achieve that by introducing a coroutine-like staging time wait instruction. So instructions defined in compute are lifted to a normal form, which basically binds the intermediate values to avoid duplicated instructions. So each instruction is basically translated into a closure, and then the sequence of closure is separated by this wait instruction. So here is an example of the same PageRank example written with the wait instruction. So we see that here we have by wait simply separates what are the instructions that are executed in different supersteps, and we get rid of the conditional branch and duplicated code entirely. So this wait instruction is actually part of it's integrated into a larger system. So it's part of DSL of the front end of our system called CloudCity. So this is a large-scale agent-based simulation framework. So here is an overall architecture of the system, and where the wait instruction is part of the DSL in the front end. So we evaluated this approach by stress test the number of branches, the impact of number of branches through micro benchmarking. And we consider both one-level nesting and two-level nesting, so you have different branching patterns. And we show that as we increase the number of branches from 5 to 20, the overall stage experiments perform better with lower variance comparing to unstaged experiments. So that concludes my talk. Thank you. Yeah, please.
Thanks for the talk. I just had a very quick clarification question about slide 12. About slide 12.
Sure.
Like the closure at the bottom there.
Yeah.
When did yield actually? When would yield become true there?
Yield is set true inside here.
Okay.
Yeah. So your question is when it becomes true?
Yeah, but I thought the compute was a different closure, or no, it isn't.
No. The
okay.
compute here is executing instructions defined in the IC.
Okay, right. Yeah.
Yeah,
okay.
yeah.
So yield is defined globally then?
Yes.
Okay.
Yeah.
Yeah. Thank you.
Yeah.
I got a bit confused. So if you go to slide 15, I think. Sorry, then 14. Yeah. So so then this is what the user will write.
Yes.
Am I right? So the SC continuation thing that you introduced. So this thing is going to be rewritten in terms of that.
Yeah. So this is the front end, and it will generate after lifting. This will generate the closures like as we show in the previous slide. So this will be the generated code, and this is the front end.
Mm-hmm. And on that generated thing, can you tell us a bit about the staging types? So which types are going to be staged away?
So during staging, right, it will analyze the program defined inside this while-true loop of compute, and when it sees this wait instruction, this we use the code pattern matching in Squid, and so when we identify this wait instruction, we will set this yield flag to true. Basically, this corresponds to my yield equals true statement, and each instruction here actually is lifted into this anormal form, which actually binds. So this will generate, each of this instruction will actually generate a closure. But then we have some compile optimization to merge the closures when they are just A goes to B, B goes to C, when there's no branching. You just merge those small closures into a bigger one. So after merging, it will look just like that. So the only continuation index you're passing is when you actually have this kind of control flow changes, or you have the yield like change of this superstep.
I see. So if I'm not mistaken, then this is the kind of final code that you will generate. You will not apply further optimizations on top of this.
Right, this is the generated code.
Okay. Any other questions? If not, let's thank Zilu again.